All right, good afternoon, everyone. So, for those of you that have seen the merge sort video, we're going to be talking about quicksort today. And it'll be a lot easier if you've seen that. So, for those that haven't, highly recommend that you go and see merge sort, or at least that you're familiar with merge sort so that you'll know what's going on. Okay, so today, since we're writing quicksort, I've created some arrays here, and I'm starting off with arrays of ints, which are increasing, decreasing, and random order. And I fill the increasing one with 0 through n, where n is however many elements in the array, and I'm doing 10. Um, and I fill the decreasing ones with basically the same thing that's in increasing, but in reverse. And then I fill the random with random elements in n squared, because that means it's less likely to have duplicates. So anyway, let's run make run. We can see here, voila, we have our 0 through 9 and our 9 through 0 and our elements here that are random. Okay, cool. So now what we'll want to do is we want to write quicksort and use it. So since we're dealing with arrays, we'll have to pass a size, but let's try and write it like we did with merge sort. So I just want to be able to say quicksort and give it the array name like increasing and give it the size, which is n. And let's do this for decreasing and for random. And then we'll print it after having sorted it so that we can see if it worked. And in quicksort, we're going to need to actually go and write these function, right? It doesn't exist. So that's in quicksort.h, so let's head on over there. So here we are, quicksort. It's got nothing in it so far. And we're going to start with just an integer only quicksort, and then we're going to do templates at the very end, same way we did with merge sort. Okay, cool. So let's write one. So quicksort, we'll take in an int array, and we'll call it r. I could have said int star as opposed to int with the brackets. I actually prefer to say that, but we're doing it this way for right now. And then it'll take in the size of the array, which we'll call n for a number of elements. Okay. And what this will do is this will call some more like secretive functions. So it'll call quicksort, which is a little confusing in that it is quicksort, but it'll call a quicksort that has lower and upper as its two indices here. So the idea with quicksort is going to be that we're going to basically want to sort the entire list. So we'll call quicksort with the ARR, with 0 is the lower, and with n is the upper. So that sorts the entire list for us. But now we actually have to go and write this quicksort function. So let's do it. So the idea behind quicksort is a lot like the idea behind merge sort, where we don't want to do anything if the list is empty, and an empty list in this case would be if the lower and upper were like the same thing. Because remember, upper being n means we're kind of excluding it, we're ignoring it. So if they were the same thing, we'd be ignoring the only value that we have, which means it would be nothing. And certainly if upper is less than lower, we would not. So let's just write a if lower is less than upper. So now we know for a fact that we're going to be dealing with a list that contains at least something in it. And what we can write is the following. So what we will do is we will basically find the partition item. So that's an item from within ARR. So we'll just write auto, because it'll be something from within ARR, and say partition item is going to be equal to the result of calling the partition function, which is the big much ado about quicksort, with the ARR and with the lower and the upper, right? So this says basically that we're going to try and partition the list. Partitioning means that we're going to try and move all of the values that are on one side of our partition element to the left or to the right, okay? And this is partition index, I'm sorry. So this is basically the location of where the partition ends up after we do the partitioning. And the reason that's important, the reason we want this as a value, and since it's an index, let's actually do it as a size type. The reason we want this value is because we're going to want to add it or subtract it from lower and upper so that we can basically deal with our list, right? So then what we'll do is we'll call Quicksort again. This is the recursion part. We're again giving it the array, but this time what we're going to do is we're going to start at lower, and we're going to go up to the partition item -1. We don't actually need to do the partition item when it is... we don't actually need to do the partition item when the partition item's already in the correct place. That's what we assume partition does. I'm sorry, I don't know why my mind blanked there, but partition will put partition item, partition index, into the exact right location within the list. That's where it will end up after all the sorting is over. So since it's already there, you don't need to sort it, right? So we can ignore it. Let's do another one. This time we're going to start partition item +1 again, because we are ignoring it because it's in the right place, going all the way up to upper. So there we go. We've now called both of our instances of Quicksort. Now, a note of caution is that I am taking a size type, which could be 0, and subtracting 1 from it, storing it to a size type. That could be positive infinity. So I don't want to do that. So let's add an extra case here that just says if pi is greater than 0. And if we think about it, if pi is equal to 0, that means the partition ends up at the very beginning of the list, which means there is no left-hand side of the list for us to sort. So we're kind of okay. We don't need to do that. And voila. Now all we need to do, this is Quicksort, we just need to write the partition function, right? So if we think about it the way merge sort worked, merge sort, we just called merge sort twice, and then we called merge, and merge is where we hit all of the intelligent parts. Partition is where we hide all the intelligent parts in Quicksort, but we do that first. Both these types of algorithms are called divide and conquer algorithms. And the neat thing about merge sort is that it divides in a very simplistic way. Just cut it in half, cut it in half, cut it in half. But it's conquer, the merge, is this more complicated thing. The cool thing about Quicksort is that its divide is the complicated part, but it's putting them back together again is actually very, very trivial because you're not even really having to put them together again. Okay, cool. So let's write our partition function. So partition's going to take in our int array. It'll take in the lower, and it'll take in the upper, like what we've been doing so far. Okay. And then what we want to do is we want to find the pivot. So there's a whole lot of different ways to try and choose the pivot. You could say the pivot is the very first item in the list, the pivot's the very last item in the list, the pivot's a random item in the list, or the pivot is the middle item in the list. And let's do the last item in the list, because this is the way I learned it whenever I was first taught. But you could really do anything. So what we'll do here is we will just say auto pivot is equal to the last item in the list is going to be at array at position upper. Okay? And the kind of trick here, though, is that remember how earlier we said that we weren't including upper? So that means it'll have to be at upper -1. So voila. And then what we will need is to have this other index that Quicksort uses. So let's create that. Size type index, which is initially equal to lower -1, which could be positive infinity because lower could be 0, but we're going to be adding to index. So it should be okay. Okay. So what we'll do is we'll say for size type I, which is equal to lower, we'll say I is less than upper, effectively. We're going to increase I, and we'll do the following. So we will say if the array at position I is less than the pivot, then that's okay, that's good. Everything that's to the left of the pivot should be less than it. So what we will do is we will simply say that we will move I forward, and then we're going to want to swap basically the array at whatever is at index and the array at whatever is at oh, I'm so sorry. We move index forward, and we want to swap whatever is at index with whatever is at I. Okay, so swap of array I and array index. Okay, cool. And then what we want to do is after the for loop, we want to do swap of array at index plus 1, comma array at the high, the pivot. Because remember we said that the pivot was going to be at upper -1, so we'll swap them just like that. Whoa. I accidentally closed the folder. Or a file, so I'll reopen it. And voila. So we're back here again. And this time what we want to do for the thing is we want to return the index plus 1. Because that's where we ended up finally doing the swap. So that's where the pivot element ended up going. Because remember, the pivot element started in upper -1, and it ends at index plus 1 because of the swap. So now we need to actually write swap. So let's do that. You know, I'm sure you guys can write swap. You've been doing it for a long time. But swap will basically take in this case, we're dealing with ints, right? So it'll take in two different int references, A and an int reference B, and we want to swap them. What we can do is we can create a new int, call it temp, and let it equal A, and then we can say something like A equals B and B equals temp, and now they've been swapped, right? Because we copied A, we then deleted A and replaced it with B, and then we deleted B and replaced it with the old copy of A. So now they are swapped. Temp automatically gets deleted because it's not a pointer or anything. And now our swap function works, and our returns will work. So that's really good to see. So then our partition function is now actually done, and we can actually test this to see, does the program work? So what we'll do is we'll go back over here, and we'd already written these tests. So let's just try running them. This is generally a bad idea. Generally, you want to test each part. Sure enough, we get a lot of issues, which is that there are too many arguments to Quicksort. So the reason is that the Quicksort that we declared, which is the very, very top here, it doesn't see the other Quicksort. It just sees itself. So what we want to do is we want to put our Quicksort kind of at the bottom. And then if we run it again, partition was not declared. Again, partition is written to the bottom here. So let's actually declare partition up at the top. So by writing this, we've now declared partition up at the top. And then we can use it. So we make run. Okay, cool. And it looks like our sort has tried to do something here, but it hasn't quite worked. It seems to mess up every other element. So what we'll do is say instead of index is So okay, we're messing up every other element. So that means that was it truly every other element? This should be 1, 2, 3, 4, 5, but we're getting 2, 4, 6, 5, 7, 3, and then the 8 is just here. You know, this is actually including, right? Because we want to exclude the partition because, again, we said that the upper bound is exclusive. And if we run, make run now, look at that, it's now perfectly in order. So silly me, whenever I was talking about wanting to exclude this one, it should be already excluded because, again, we said that we were going to do that. That's what this was doing. So by doing the -1 there, it was no longer being excluded. And we don't really need this anymore, although technically still a good idea, because we would do, if pi was 0, we would do the -1 over here and access immediately, which is a segmentation fault. So we wouldn't want to do that. So this is still a safe if statement to have. We're thinking correctly whenever we put that in. But now we have a quicksort. It seems to be working because the data seems to be in order. But let's write some tests for it. So I wrote some tests with merge sort. Let's try and do that same kind of thing again. So we'll create a boolean here and call it sorted. And what it'll do is it'll take in an int array of size n. Okay? And it'll take in... that's it, actually, because the n is already brought with us here. We know that this is 10. So what we can do is we can simply say for int I is 0, I is less than, n plus plus I. There it is. And let's actually make I a size type, even though it really doesn't need to be here, but I kind of like to. So then what we can do in here is we can say something like if the array at position I minus 1, but remember we have to start I at 1 if we're going to do that, is greater than the array at position I, then we'll just return false. But otherwise, after the loop's over, we can return true, because that means we've now gone all the way through the array, and we haven't found anything wrong, so we're pretty safe. Let's create another one here, and this one is going to be the contains same. So what we'll call this is now set equivalence, because if we think of the array as being a set in a mathematical sense, equivalent sets have the same number of elements and they have the same elements within them. So we'll have two arrays. We'll have the expected array, and then we'll have the int actual array. Okay, and then what we'll do is quite simple. We'll just say for I is equal to 0, I is less than n plus plus I. We'll say for size type j is equal to 0, j is less than n plus plus j. And we'll say the following. Bool found is false. And if array at I is equal to array at j, then let found be true. And what we can do is we can actually go up here to our condition for the loop, and we'll add an and found is false. So as soon as found becomes true, we'll stop looping. And then what we can do is we can say down here, if it's not found, then we know that they aren't equivalent, so we can return false. But now we've got to rename these because I wasn't paying attention. So expected should be the first one, and actual should be the second one. And what this is doing is it's going through every element in expected, 0 through n, and every element in actual, 0 through n, and checking to see that it's got at least one of each. Now, you could theoretically get around this by having a case where they have duplicate elements, and the one was, say, missing one of the duplicate elements. But it's not technically that important. So this should be good enough. Especially because both arrays are guaranteed to have the same total size, both size n. So let's see. Let's actually, tell you what, no, let's fix it. Let's actually fix it. So what we'll do is we'll say size t occurrences, which is initially equal to 0. And if the expected at I is equal to the actual at I, or j, then the occurrences will increase. Whoa. Terribly sorry about that. And if occurrences is 0, then we'll return false, because we would expect that whatever is located at I appears in J the correct number of times. And let's also write here J is 0. Expected at I is equal to expected at J. So the occurrences is 0, and the expected occurrences is equal to 0. And then what we'll do in this case is we'll just increase the number of expected occurrences. And then we can say if it's not equal to the number of expected occurrences, then we'll return false. So what this says basically is we figure out how many times does the thing appear, how many times should the thing appear, are they the same? Okay, are they not the same? Uh-oh, we've got a duplicate or a missing, one or the other. And then we'll return false, otherwise we return true. So anyway, this should theoretically work. So now what we can do is we can throw those in here. So what we'll do is we'll just copy paste the quicksorts and select, and select them like so. And we'll now do a, we need to write a test function. So void test, which will take in an int r of size n. And what it'll do is it'll create a new int copy of size n, and it'll just do for int I is equal to 0, I is less than n, plus plus I. A simple copy at I is equal to array at I, like that. And let's technically do this as a size t. And then all we need to do is we need to say something like quicksort of copy with n elements. And then what we can say is if not sorted, copy, or not set equivalent from the original, which is ARR, to the copy, then throw a standard runtime error. And we'll say either not sorted or missing / duplicated values. And of course, to use runtime error, we're going to need to include exception, which we have done up here. So now what we can do is we can change these all to say, I think I called it test. So now we test them. We don't need to pass it the n, it just knows. Okay, cool. So now we can run our make run. And we can see here the program runs successfully. And if we go into test and we comment out quicksort, so it's not going to run quicksort for us, we make run, the test fails. So, because the list isn't sorted. So there we go. So that is our quicksort, written about as quickly as we did for merge sort, probably a little faster. Let me look at the time. Yeah, actually, wow, 10 minutes faster. We were flying through, even though I had a few moments where I got stuck and needed to debug. Cool. So I'm going to be putting all this code up on GitHub. You can go and find it. The link is in the description of this YouTube video. Feel free to have any comments on the video if you have questions, or you can raise them as issues on the GitHub. But this is Quicksort. So now, for those that want to stick around for the template portion, we'll get into it. So under quicksort.h, let's change this to work with templates. So we'll say template type name t. Oops. So now instead of an int array, it'll be a t array. And let's make all of the functions templated. So again, it'll be a t array. And a t array, 2 t's, a t. The pivot's already an auto, so that one works. A t array, and yes, this is looking good. So our quicksort theoretically now works for templates. So let's try and make our testing templated as well. So testing will now work with a template. Set equivalence will now work with a template. And sorted will now work with a template. So voila. We now have all of these different functions, which now work. And we can theoretically now try it with strings, but let's see if it compiles. It does. So let's now create a char star random of size n, and we'll call this phrase because it'll contain strings. Strings are char stars. And what we can do is, well, actually, char stars are not comparable, so this will actually fail. So let's actually use the string that's in C++. The way you can get that is you obviously go up and include string, and you should use standard string if you want to type it without the std. Oops, string, just like that. So there we go. We can go back down here, string phrase n. And now we can say the following. Phrase at 0 is going to be hello. 1 is going to be there. 2 is going to be my. 3 is going to be name. Whoops, 4 is going to be is. 5 is going to be Dante. And the rest of the phrases, I don't really want anything in them. So let's try and null them out. And this will be a good test to see if you're allowed to just have a null and see if that works. So 7, 8, 9. So this goes and puts in all of our different phrases. And then what we'll try and do is we'll try and see out the phrase. Cool. And we'll try and see it out before and after. We'll then test the phrase. And we'll quicksort the phrase. And let's see if this works. Fingers crossed. So make run. And we can see, hello there, my name is Dante. The nulls come first in sorting order because null represents the number 0, and 0 is less than all of them. So whenever we do strings, the zeros come first. But then we have Dante, hello is my name there, which is the same order I believe that we had with merge sort. If I picked the same string, I can't recall. But this is in order. So that's very good to see. And what we could do, if we wanted, is we could try and not put in these nulls, and we could see what happens. This could, I don't know. So it seems to be that they're nulls anyway, which is good. But yeah, so that is kind of the templated version of Quicksort. So again, what we did is we had to go and convert it to a template. We had to go change all of the ints, t's, and then our Quicksort works on these templated types. So very, very nice. And this works obviously on pure arrays as opposed to vectors, which is what we did for merge sort. So wonderful. Then I guess that's all that I've got. Have a wonderful evening.